Well, hello everybody. Thank you for joining us today. My name is Ian Mosley, and I'd like to welcome you to the first of our series of Powerful Knowledge, series of power electronics training that we're going to take part in over the next few months leading up towards the end of the year. I'm delighted you could join us today. We're very excited to be able to deliver this set of online training. This is a live event today. We are recording these, so if you miss anything, you will be able to access the content on demand afterwards. And the same goes for all the webinars that we're delivering in the future. You'll be able to get links to all of those. So in this particular webinar, I'm going to be talking about really what we plan for the entire series that we're going to be delivering to you over the next few months. It's going to be a rather high level overview. We will go into some technical detail, but most of the technical detail will be in the further webinars. But I'm pleased you could join us today where we can give you an overview. The format for this webinar is that each webinar will be about 1 hour long, including about 10 to 15 minutes of questions at the end. If you look to the right-hand side of your screen, you'll be able to enter questions into the question box, which we will do our best to answer at the end. And if any questions we don't have time to answer, we will take offline and respond back to the people who entered those independently. There's also a chat box. You can put some text and bits and pieces up there should you want to. And we're also going to be running a number of polls during the course of the webinar, just to get a feeling on the background capability you have in power electronics, the areas you're interested in, and also how effectively we're communicating this content and how accessible you're finding it. So thank you once again for joining us today. I'm lucky to be joined by two other guests today on the webinar. The first is Assistant Professor Jose Gonzalez from Warwick University. Jose will be presenting some content in later webinars, so I'd like to just give Jose a chance to introduce himself.
Hi, hope you hear me well. I have some issues with the microphone, so let's see if you can hear me properly. So I will be covering some advanced characterization of wide bandgap power devices, namely electrothermal characterization of silicon carbide power MOSFETs, reliability, condition monitoring, a bit on packaging. Focusing on reliability, it will be gate oxide reliability of silicon carbide. So hope you enjoy and you join the webinars the next weeks.
That's great. Thank you very much, Jose. We're very pleased to have you joining us, and you're going to have some very interesting content for us. I'm going to present a few slides, and then I'll introduce our second guest, a gentleman called Dr. Will Drury, who's kindly joined us today, who's going to tell us a little bit about the funding landscape in the UK for power electronics and some of the exciting things going on in the funding for these advanced areas of technology. So I'll just quickly move over to a few slides. Okay, so this first webinar, we're branding this overall series the Powerful Knowledge series, and it's it's an online technical training in power electronics. The main aim of this set of webinars is really to provide access to expert online technical training in power electronics. We saw an opportunity with the current pandemic situation to utilize the time to deliver technical content online, and that we're hoping that this is a way we can start to offer online technical training in the future as well. So hopefully this will be very interesting for people. In terms of the relevance to our audience, the content we're presenting today and over the rest of the series is going to be very useful for design engineers who either wish to move into or want to upskill in power electronic design. So if you're working in electronics and you want to know more about power electronics, watch the seminar. We're going to cover so many different areas that might be useful for you. We're also trying to balance parts of this webinar series to make it accessible for people who don't necessarily work hands-on in power electronics, but might be leading the projects or the teams that do want to exploit and utilize latest generation technology in power conversion. So hopefully we present it in such a way that if you're in that category, you can start to see the performance levels that are now achievable in the very high performance techniques that we can use in power electronics. And I thought I'd also mention this might be useful for field applications engineers. I used to be one myself, and these field applications people are the guys that or the folks that go around visiting customers and supporting them developing their power converter systems. And the reason it might be interesting is it gives a more broad, this course will give a more broad perspective on the types of technologies that the technology they're providing fits into. So hopefully this will be quite a useful series of webinars for these particular people. So we're starting off today with our introduction and our overview. This is really just to give you a feel of what to expect over the rest of the webinar series. And then we're going to start moving straight into the more advanced technical information. So on Thursday this week, I'm going to be hosting a webinar talking all about the power topologies that you might find commonly used in advanced power conversions. So whether we're converting from AC to DC, or DC back to AC, or even DC to DC conversion, there's quite a few key topologies that we want to describe about and describe how they work. So we're going to be covering that in our topologies session on Thursday. Moving on through the series, we're going to then start talking in quite a lot of depth about power semiconductors. In recent years, there's been a real a step change in the performance capabilities of power semiconductors with new types of wide bandgap devices available. And that's why Jose is joining us as well, because he is a real world specialist in one of these particular types of wide bandgap technology called silicon carbide. And it's something we use here as well. So Jose will be going into a lot of detail on some aspects of these devices. Then we'll be moving on to magnetics design, and as you'll see, the magnetics design is something that's becoming absolutely key if you're trying to squeeze the last % of performance out of your power converter system. And it's partly been driven by the fact that new wide bandgap power semiconductors allow us to push the switching frequency of power converters ever higher. And the benefit of that is we can make it smaller, but you can only do that if your power magnetics and your passive components can keep pace with that. So we'll be discussing some really interesting aspects of magnetics design, including fundamental equations, material properties, finite element modeling, and different loss mechanisms. So that's I'm quite looking forward to delivering that set of webinars. It's going to be an interesting journey, that one. Thermal design is absolutely key. Pretty much any power electronic system ends up being thermally constrained. And even if we develop and utilize new types of technologies which allow us to push the efficiency of our power conversion process ever higher, what you tend to find happen is if as an engineer you make something more efficient, then either the product designers want you to make it then smaller, or perhaps put more power through the same platform. So you end up becoming thermally constrained again, just at a different operating point. So thermal design is and always will be one of the key aspects of high performance power electronics design. And we're going to have a dedicated webinar talking about different ways we can manage thermals in a system. Simulation is sometimes a contentious subject. I think it's a fantastic tool for predicting and de-risk, or predicting the performance of your converter and de-risking the hardware development. But you've got to be careful. You've got to be careful how you use it. And we're going to be talking in depth about some of the trade-offs that you can have with simulation, some of its strengths, and how you can use it to best effect in your company. Reliability, if any of you have been working in power electronics or even just general electronics for some time, it's often the power converters that tend to be the weak point of a system. And the reason for that is they're the parts of a system which are subjected to the highest temperatures, the highest voltage levels. They contain a lot of energy that's moving around very quickly. So they tend to be the part of a system that's the most stressed. So it's very important to understand what drives reliability in power electronics and understand some of the different failure mechanisms. And we're going to be talking about some of those failure mechanisms in that course, in that webinar, and also how to model lifetime based on scientific methods, if you like, so you can start predicting field failure rates and population failure rates, that sort of stuff. So that's a very important area of power electronics. System architecture. When you're moving up to much higher power level systems and higher power, especially with digital control, how you architect and partition your system becomes very, very important. It has an impact on your risk profile of developing that system and where you put fault protection, that sort of thing. So when you're developing a high power electronic converter, it's important to have some idea around how system architecture can really help you. So we're going to talk in some depth about some of the trade-offs that can be played there. Closed loop control. This is one of my particular favorites. It's any power converter, or nearly any power converter, requires closed loop operation. So if it's an offline power supply, it might be regulating a 48-volt rail or something like that, irrespective of load up to a certain level or input mains fluctuations. To do that, you need closed loop control. And there's a number of, well, there's two main ways of doing that: analog or digital control. We're going to be talking about both of those in one of our, well, actually in two webinars. And this is probably where the webinar series becomes the most mathematical, because you need to start modeling closed loop responses and small signal behavior and things like that. Don't let that put you off. We'll try and describe these key ideas from a conceptual standpoint, and then we'll use maths just to support those concepts and show you how to work out the answer. The key thing is to understand how the system is controlled. Moving on, regulatory and compliance. This is a key one. As you'll see later on in this webinar, switch mode power converters work at high frequency, so can generate noise. And part of what you have to do when you're developing your power converter is to mitigate that noise and make sure you don't exceed the regulatory levels. The trouble with EMI is often it's left to the last or towards the end of a product development, where it's very, very expensive and difficult to fix. So we're going to discuss how you can use early stage rapid prototyping to start getting a feel on EMI levels, and also some techniques around mitigation of those noise levels. And last of all, I'm quite looking forward to this particular webinar, just some practical tips and tricks, things we've learned over the years working on various different converters that can help you debug them, bring them up to, and get them up and running in a way that just allows you to be more productive. So, for example, here on this scope probe here, taking a measurement when you've got high common mode noise, it's a good idea to put your scope probe through a common mode coil just to reject common mode noise. Things like that can really be quite useful when you're debugging a converter. At this point, before I dive into the rest of the content of our presentation, I'd like to give Will an opportunity to just briefly introduce himself and tell you about some of the aspects of funding in the UK. Over to you, Will.
Thank you ever so much, Ian, and really, really pleased to be able to join you and everyone you've got on your webinar at the launch of what sounds to be a really, really exciting adventure that hopefully everyone is going to join you on across the between now and Christmas with some really interesting technical content. So I really appreciate also the fact that I can come and talk to you about what we're doing in driving the electric revolution. So we are part of UK Research and Innovation, delivering part of the UK government's industrial strategy. So we provide funding to organisations, etc., to deliver technology to grow and allow that to happen. So really pleased to be associated with what you're doing here, and really hopeful it's going to make a big impact within power electronics machines and drives. I am a power electronics machines engineer background, really excited to see this taking off. So this challenge fund has money to give out. That's a really important element of it. We invest in supply chain growth for power electronics machines and drives. That's really important. We come up with some great ideas, but how can we actually make them? How do we pull through that research? Within the challenge, we are covering all sectors. We have industrial drives, robotics, energy, marine, as well as the sort of transport sectors there of aerospace, rail, and automotive. There's a lot of synergy there. Certainly when you start talking about some of these converters, Ian, and I see looking at buck boost converters, does it matter which application they're going in? There's going to be nuances of the design. There's going to be vibration specs are different, an EMC spec, maybe some of the, but actually maybe the silicon carbide device itself down at device level is similar. So it's looking at these synergies across all these types of activity. And we are looking across that whole spectrum, from the raw material through to system integration, across power electronics, machines, which I appreciate you're not covering here, and also drives. So how do we put intelligence around power switching devices, from raw material, ingots of silicon, silicon carbide, gallium nitride, all the way through to integrating this into a system. And that whole thing together is really important. And there's only certain areas, though, that are going to provide significant value. And they're the ones that we're interested in investing our money. And I say investing money because that's what we're doing. We're not just giving money and great. Look at that investment opportunity to bring people together in a collaborative nature. And it'd be remiss of me to go on and let you carry on, Ian, without sort of going back to, we talked about a load of the detailed technical stuff, but we've also got to think about how those design decisions impact the life cycle analysis and also the environment in the world in which we live. And that is really important. And what you're talking about here, it's exciting because it is an underpinning technology of net zero, of the future. We can't generate energy without these converters. We can't use it without these converters. It is fundamental to net zero and decarbonisation of the future. And so is how do we reduce the reliance on new material through that recycling. Talent, I've been in the hiring line, trying to find talented people. We've got a good number on board today, and I've seen from some of the polls here that we've got people that are new to this. It is really exciting, so please don't go away at the end of this. But we need more trained engineers across all levels. What you're supporting here and the quality I know from the time we've spent together in the past is going to be fantastic. We're going to learn some real detailed stuff across the spectrum. We're also investing in the level 4, 5, and 6 skills, which are essential as well for the supply chain growth. So all that coming together with what you're doing here is really important. And we're looking at cross-institution. So we're not after just one place that delivers everything. How can we deliver the best across a really good platform? We've also invested £30 million to date on industrialisation centres, adding to the network of open access equipment already within the UK, so that can be accessed by companies across the world to come and use around different technologies needed for the manufacturing and supply chain growth of power electronics, machines and drives, and to be able to signpost people to other areas in the UK that already have some of that equipment. So that in itself is going to grow and grow, and we'll have more information on that. So I'm not going to take up any more of your webinar, Ian. I would say you talked about simulation earlier. Hopefully you'll be able to, we're on together on a webinar in a week or so, week and a half time, talking about that simulation versus making element with a few other eminent people that I'm bringing together from around the industry and academia. So if anyone on here is of interest, if you Google Driving the Electric Revolution and KTN, then you'll be able to find somewhere to sign up for that will come online in the next little while. Please sign up to our newsletter. Reach out to me. Join us on a road to net zero. Ian, thank you for the opportunity to come and talk to your attendees here. And I wish you all the success with this webinar series. I'm really excited to see where you end up in the near future.
That's great. Thank you so much, Will, for your words there. Yes, we're very excited to be delivering this. So I'm going to dive now into a little bit more technical content. I've kept you waiting for a little while, so let's get started. Oops, I say, let's make the right screen. So background on switch mode power conversion. Now I appreciate this is probably, if you've worked in power electronics for some time, I apologize because this is going to be rather a basic introduction, but I want to define what I mean by switch mode power conversion by defining what it isn't. So on the left-hand side, well, in fact, the two pictures here, you're seeing two circuits that can perform the same function, converting a high input voltage down to a low output voltage. And it's a very basic application, but it helps to highlight the differences between the systems here. So on the left-hand side with linear conversion, this is used all over the place and it works very well for certain applications. We have a power transistor or a power device, which essentially, if we had a 28 volt input on the input to this linear regulator and we're regulating to 5 volts, all that happens is that linear regulator drops the difference between the two. So you'll have 23 volts across the linear regulator. And it has feedback control here. So this thing turns itself on a little bit more or off a little bit more just to maintain the output being constant. So it operates the transistor, the pass device there, in its linear region. And it works very well for low power. The trouble is, if you have any sort of big difference between the input and output, the efficiency of a linear converter stage, as shown here at least, is just the output voltage divided by the input voltage. So it's great for just a few milliwatts here and there, but if you're starting to push any level of serious power, this just doesn't work. It just wastes too much power. So great for board level, low power rails, that sort of stuff, but for high power, forget it. That's not any going to work in any sensible fashion. So the circuit on the right-hand side here, this is just a simple buck converter. It's one of the most basic topologies you could find, and it's very commonly referred to in literature. And I just put it up here because it's a nice simple circuit to explain the concept of switch mode power conversion. It operates slightly differently. It's performing the same function in that we're reducing a higher input voltage and generating a lower output voltage, and we have a pass transistor. What happens now, though, that device, that pass transistor, is operated not in its linear mode, but in either it's fully saturated or it's on state or in its blocking state. And it's turned switched between those two states at high frequency using a modulator circuit. And there are different ways you can then play with the ratio of the on time to the off time to control the output voltage. So bear with me on this. That's just the concept of how that switch mode power converter works. Ideally, we now want the power transistor and the diode here to be ideal components or perfect elements. And I'll describe what I mean by that in a few slides' time. The rest of the circuit here is actually what it's doing is it's an energy store, a high frequency energy store, such that the high switching frequency generated essentially across the diode is then filtered to recapture a lower output voltage. And I'll show a little bit more detail of how that works in a moment. But essentially, a switch mode power converter has semiconductors which are running at high frequency, coupled with inductors and capacitors which are used to buffer and store that energy and return DC to the output. In the theoretical case, if both Q and D were those ideal components that I'm talking about, and the inductor and the capacitor are ideal components as well, this conversion process is 100% efficient. Obviously, that never happens in practice. There's nothing as good that you can never get to 100% efficiency. However, as devices approach the ideal that we're describing in a moment, we can start getting closer and closer to that theoretical level. Well, let's move on to the next slide. So hopefully that's a useful example of a switch mode power conversion system. Now, if we take that buck converter and we start to put some of the other bits and pieces around that we're going to have to use to make this thing work. There's our basic power stage that we've used in the previous slide. The first thing we need to do is to put a gate drive circuit onto that power device. And the purpose of the gate drive circuit is to either hold the device Q in its on state or hold it in its off state, and also to move between those two states as quickly as it possibly can. Other than that, the gate drive doesn't have any other intelligence there. Its job is just to take an input signal that is used to turn that device on and off. It's like a buffer stage. But actually, as I'll describe a little bit later, that gate drive circuit, when you're using wide bandgap semiconductors, becomes an absolutely critical part governing performance of your system. And I'll explain why actually in one of our later webinars. It might look like a simple little circuit, but it performs a key role. The input to that gate drive circuit, we have to generate this on and off signal to feed into the gate drive to tell it what to do. That comes from a modulator. And the role of the modulator is to take a much lower frequency constant signal, or a signal that's moving up and down slowly, and turn it into a series of on-off commands to tell the gate drive to turn the power device on and off And there are different ways that modulation scheme works. One of the most common is pulse width modulation, which I've got a slide in a moment to talk about. In a pulse width modulation system, we run the device at a constant switching frequency, and we just change the on to off time of the switch to give you a variable duty cycle, and that's how we control it. But there are others as well. The modulator, though, doesn't have any intelligence. It takes its instructions from a system controller, and this is the part of the power converter that has more of the brains in it, if you like. So in the case here, I'm showing that controller taking the output voltage of this converter. So if it's the 5-volt converter, you would feed that into the control circuit. The controller will then compare that to a reference, run it through a compensation network, and generate the demand for the modulator signal. So if, for example, your output voltage was too low, the controller would recognize it's too low and start demanding a higher input onto the input to the modulator, which then increases the gate drive of the power stage. If it's an analog controller, that's fairly straightforward. If you have a digital controller, it does the same, but it's using software instead. But then you can start putting digital communications into the system as well. So that offers some other system level advantages. The controller can operate on any parameter or all sorts of parameters in the system, especially when you have advanced digital control. So if we take the input voltage and use that as a reference, we can start implementing feed-forward control. So we can actually use that as a variable into our control algorithm. There's a whole series of control schemes based around peak current mode control. And in peak current mode control, the controller also has knowledge of the current, the cycle-by-cycle current flowing in the primary magnetic storage element, or some representation of that, and that can offer some transient response improvements because you're essentially directly measuring the energy in your circuit. And we'll talk a little bit about those control algorithms in our later webinars. Also, when the power stage is running, it's generating heat, and we need to manage that heat energy. So we might have passive cooling here. We could have an active cold plate. Essentially, the controller needs to know also what temperature the system's running at, because the controller itself might then choose to derate the output. If the temperature goes above a certain level, it might either reduce the output voltage, or it might actually just decide to turn the output voltage off. Or maybe it makes a decision then to turn a fan on to blow some more air over that heatsink. So you're starting to see the controller here becoming a key critical part of how this power converter is managed under normal operation. The EMI filter I'm showing on the front end here, that is an essential part that is sometimes overlooked in literature. Any of these switching power stages, as I've described before, generate high frequency noise, and you tend to find you need to use an EMI filter. Certainly for any reasonable power level you will. That EMI filter tends to sit right on the front end of the power converter, but you can have distributed filtering as well. So designing and knowing how to go about designing the EMI filter is a key part. So in terms of our webinars, what we're going to be talking about, we'll spend a large part of the webinar time talking about aspects of the power stage design. So I've already mentioned topologies. We're going to spend quite some time discussing some of the more popular topologies, both isolated and non-isolated. We're going to be talking about power semiconductors, and that's why we're very lucky to have Jose joining us, because we're going to have a real deep dive into some of the performance of wide bandgap semiconductors here. Magnetics, we're going to spend quite a bit of time talking about magnetics. So they're all related to the power stage design. Believe it or not, we're going to have an entire webinar dedicated to gate drive, and the reason for that is, as I indicated earlier, it's a key part of the system, and at high power it bridges two different domains. It's sitting between the very high power, noisy, hot, nasty environment of the power stage, and the other side of it is connected to low voltage control electronics, and it's bridging those two domains, and it has to do a very timing critical job, and it's very important how you design that gate drive. So we'll have an entire webinar talking about some of the ways you can design gate drives to give you high performance. I've already mentioned we're talking about analog and digital control. That'll be further on down in the series, and increasingly these days, certainly for higher power systems, digital control is really the way to go, because you can implement all sorts of non-linear control, pulse mode operation, and you can redefine behavior in software, which is very difficult to do, obviously, in an analog system. So I'm looking forward to talking about those particular aspects. I've already mentioned thermal design. We're going to have a dedicated webinar on thermal design. That also links into reliability as well. So those two things are fairly tightly coupled. We're going to have dedicated webinars on EMI, both from a theoretical side, causes of EMI, and how to design filters, but also some practical tips and tricks. If you've worked in EMI and you've been fortunate enough to have to debug a power converter that's failing EMI, you'll know that it's quite a challenging thing to do sometimes. So having an armory of practical techniques and methodologies to help steer you through to a compliant solution is something that's really very useful, and I do hope that'll be useful for you if you can join those webinars as well. Okay, now this slide, I hope you like the analogy that I'm about to use. It's something I've used many times now with customers to explain how switch mode power converters work. Not everyone likes this analogy, most people do, so bear with me on this, and hopefully it's quite a nice way to express how switch mode power converters work. And my take on this is switch mode power conversion is all about energy. It's about how energy is stored, transmitted, manipulated, and controlled. And in my analogy, in my happy world here with my bucket, the water in my bucket represents energy in our converter. The bucket itself represents the energy storage system, which in the world of our power converter actually is our magnetic component typically. The amount of water we transfer per second from the input side to the output side of this converter represents power throughput. Now, each time the bucket manages that transition of water from the input to the output, or in our power converter, energy from the input to the output, some of the water or energy is lost, and that represents the inefficiency in a power converter. The reason I quite like this analogy is there are a few key things that you can then, or key points you can conclude from that. Firstly, if you can transfer more buckets per second of water from input to output, it means you get away with a smaller bucket. And the direct correlation to that in the world of a power converter is that if you run at a higher switching frequency, then to a certain point, you can make your passive power components, particularly the magnetics, smaller, so you get better power density. It's generally more efficient if you can fill the bucket full each time you transfer it across to minimize the impact of lost water. And that's how you can go about maximizing the conversion efficiency. And that you can look at that from a point of view of systems whereby you're trying to meet requirements on standby consumption or maintaining high efficiency at low load. You can start using frequency reduction techniques to maintain high efficiency. I like this analogy. You need to make sure your bucket doesn't leak too much, and that's directly comparable to trying to minimize the loss in magnetic components, because your magnetic components is generally what's storing the energy whilst you're transferring it. You should also try not to spill much water when you fill and empty your bucket, and that correlates to minimizing semiconductor loss. So I think this is quite a useful way to describe the power transfer process. I'd be very interested in your comments on this. So if you like that concept, maybe just put a little note in the chat box. If you think it makes sense, I think it's quite a nice way to express how power converters work. In terms of then what happens in a real power converter, this is an example plot from a buck converter I actually had on the bench. This particular buck converter was running from about a 30-volt input down to a 5-volt input, a 5-volt output, at up to about 1 amp load. And the reason I quite like this as a demonstration is this particular controller that that's utilized in this buck converter has a variable frequency operation. And the plot on the left-hand side here shows the switching node of that converter, which gives you an idea on energy transfer under no load conditions and under full load conditions. So if we start on the left-hand side, under no load, you can see I'm measuring on the scope a pulse of energy being delivered. Well, it's about 412 nanoseconds long, and it's being delivered at a repetition rate of 80 hertz. Now, that might sound like that's quite frequent, but it's not. That's a very, very low repetition rate. So under no load, what's happening in this converter is that about 80 times a second, you have a 412 nanosecond pulse of energy being delivered through to the output. And the rest of the time, the converter's not doing anything. Now, that means you don't suffer much switching loss. So if you actually look, each of those pulses of energy is about 3.4 microjoules. So it sounds like a tiny amount of energy, and actually it is. The power throughput in that case is your 3.4 microjoules multiplied by 80 hertz. So we're transferring about 300 microwatts of power through to the output. But remember, on the output, we don't have any load. So actually the power you're seeing there is really just bias loss in the system and probably the output current drawn by your sense resistors. This allows you to have very, very low standby consumption. So you can get to tiny, tiny power levels. And that's important. These sorts of techniques are used for offline mains power supplies. So if you're charging your phone, you leave your charger plugged in the wall and you just unplug your phone, there are regulations and Energy Star stipulations around the energy consumption that you have to meet. And they're very low these days, around the 10 milliwatt level. So this is how those converters tend to achieve that. They run at very low frequency under no load. However, now look under what happens under full load conditions. We've got the pulse, which is about the same pulse length. So the pulse is, in this case, I measured 468 nanoseconds. So it's a little bit more, but it's about the same. But look, the repetition rate has gone up from 80 hertz to nearly 400 kilohertz now, which is the fixed switching frequency of this converter. Each of the pulses actually got a little bit more energy. So compared to no load, we've got probably about 3 or 4 times more energy in each pulse, so 12.6 microjoules. And the power throughput now is just the product of those two. So we get 5 watts output. But you can see we're getting far more power output now because we've just got more little buckets of energy per second going through. And the most important thing is this maintains high full power efficiency. So we've got the best of both worlds with this buck converter. We've got very high efficiency under full load conditions, but under no load conditions, the power drops right off. It's almost like the ideal converter. In terms of the building blocks, I've mentioned in the start of this webinar the ideal components, and the building blocks here that I'm showing you are the ideal switch and diode, and I want to define what I mean by that. So on the switch side here, what I mean by ideal is this component has infinite impedance when it's opened, and it can stand off an infinite voltage. When it's closed, it must have 0 impedance, and it can support an infinite current. And that subject to the control signal, it can move infinitely quickly between those two states with 0 energy loss. Also, we want to make sure, for various control reasons, that the transition between states occurs with 0 latency, and that comes into play in when you're starting to model closed-loop performance of power supplies. If you've got a big delay on your control signal to when this actually does change state, that introduces phase lag into your system, which can cause instability, especially at high switching frequencies. Lastly, in my ideal switch, I wish I could get one of these. It's also got 0 power drawn from the control signal. So that's what I mean by an ideal switch. Similarly, an ideal diode is a little bit like that, except it doesn't have any control. It just conducts an infinite current in the forward direction with 0 voltage drop, and it blocks an infinite voltage in the reverse direction with 0 current flow. And again, it transitions between those two states infinitely quickly with no energy loss. Now, it'd be nice if we could buy those parts, but for various reasons, they will it'll never be possible to make those. So the key thing is to understand how power semiconductor devices that you can actually buy differ from these idealized conditions and these idealized parts, because your job as a power electronics engineer is to understand how to manage those differences in performance and make your converter actually work properly. I won't go into too much more detail other than to say in our 4th webinar of this series, I'm going to be talking all about different power semiconductors, and the main focus is going to be on explaining how some of the common devices like IGBTs, silicon MOSFETs, or wide bandgap gallium nitride silicon carbide devices, how they differ from that idealized model, and how you therefore have to manage their behaviors in a real system. The second building block that I just briefly want to describe is the modulator block. And if you remember back to the earlier slide, this is the part of the system which takes a constant low-level signal, the output of your controller, and turns it into the switching waveform to be sent to the gate drive. And the pulse width modulation is probably the most common way of doing this, and that you can implement that just with a comparator, whereby you have a sawtooth waveform on one pin and you feed the low frequency continuous signal onto the other pin. So you can see what that then generates is a fixed frequency series of pulses, and as your demand signal goes up, the on time relative to the off time starts to increase. And that's how you can control under pulse width modulation. However, if you remember that example I gave on a slide or two back, if you run down to 0 load, you don't want your power converter running at 100 kilohertz anymore. You want it to back right off. So there are some schemes that can mix these two schemes together, but another scheme is a pulse frequency modulation system. And what happens there is that we have a one-shot timer. So the modulator generates a fixed on-time pulse, and then it varies and modulates the off-time of that of the system to control the duty cycle. So as you wind the load up, the frequency moves higher and higher and higher. As you move the load down, the frequency starts to drop off. But the fixed pulse width is what you'll tend to see on the scope, and that's similar to what you saw a minute ago. Passive power components. These are like the poor cousins to the advanced semiconductors that everybody gets excited about. And modern semiconductors are fantastic. However, as I said before, you mustn't forget about the performance of passive components. And it's good to understand how energy is stored. And power conversion, switch mode power conversion, is all about the manipulation and control of energy. And the inductors and the capacitors are where those pulses of energy are stored when you're switching power transistors on and off. So firstly, capacitors. Apologies if this is rather basic, but a capacitor stores energy in the dielectric material between two parallel plates. And the energy stored in that capacitor is just a half CV squared, where V is your voltage and C is the capacitance. If you actually find out, you can find out that the capacitance is given by epsilon naught, epsilon R, A upon D. Epsilon naught is a fixed constant. Epsilon R is the relative permittivity of the dielectric material between the two plates. A is the area of the plates, and D is the distance between them. So we put that in this equation, we get an energy storage capability, which is given as you can see on the screen here. So for a given fixed surface area, you can store more energy if you can use a dielectric material with a higher relative permittivity or a smaller gap between the two. The trouble is that dielectric materials will always have a breakdown voltage. So if you try and make your dimension D too small, you'll find you wouldn't be able to store the same, you wouldn't be able to have the same voltage across it because it would break down. So actually, there's a real balancing act to be struck between dielectric materials and how you make these parts work. But fundamentally, that's how energy is stored in a capacitor. The electrolytic capacitor is just winds of foil with a liquid electrolyte between the two and a separator paper, but that can actually cause problems because the electrolyte dries out over time, which then feeds into the whole prediction of reliability. Ceramic capacitors, they use a ceramic material with layers of metallization on them, and the relative permittivity of the ceramic material gives you your capacitance, but you can't store as much energy generally in ceramics compared to electrolytics. If I briefly now move on to magnetic components, so inductors, transformers, that sort of thing, they store energy in a magnetic field rather than an electric field. And the energy level is just a half Li squared, where L is the inductance of the inductor and I is the current it's supporting. You can work through the various equations to come up with this, this representation of what that energy looks like. And all of these magnetic components are formed by coils of wire on a, well, in an air core inductor, there's no core, but generally you have some magnetic material in there which has a certain relative permeability. This equation, if you look at it, the energy is directly proportional to the product of LC and AC, which actually LC is the length of the magnetic flux lines and AC is the cross-sectional area. So LC, AC is the volume contained or where the magnetic flux lines are contained. B is our flux density, so that's the number of magnetic flux lines per per unit area of cross-sectional area. Mu naught's a constant. So you can see here, if we want to store a lot of energy, you want either a lot of volume or you want a very, very low mu r. So you might think to yourself, well, why don't I just use air? Mu r is 1 for air, and actually air is the best storage mechanism for a magnetic field. The trouble is that if you just had an air-cooled inductor, you need to put a huge amount of turns of wire to get any sort of sensible flux density. So normally you end up putting an air gap into a magnetic material to give you like a way to trade off those two different things. But essentially it's storing energy in a magnetic field. And again, we're going to be talking in depth about how to go about designing those magnetic components in later webinars. You can't really design your own capacitors unless you've got a specialist supplier or something like that. So you normally just have to buy those and specify them correctly. However, with inductors and transformers, it's really, really key for good power electronics to understand the principles of how to design magnetic components. And I'm very much looking forward to going through that on our later webinars. Real world operation. Okay, so you can see in the real world, we don't have quite the idealized waveforms. I'm coming back to our buck converter example here because it's quite a nice one to talk about, and I can get waveforms from the bench. So for these particular scope plots, I'm showing continuous conduction mode. So I've loaded up the output to be high enough that the current flowing in the inductor never drops to 0 in a switching cycle. So that's continuous conduction mode. And I'm capturing the switching node voltage. The yellow trace is the switching node voltage across this diode. And then the red trace is the current through the inductor. And then below that, I'll talk in a moment about discontinuous conduction mode. If I focus now on what the idealized waveforms would look like, the ideal waveforms, this would be a pure square wave on the top, and this would be a pure triangle wave here. And actually, it's not far off that ideal theoretical model, except if you start looking at some of the edges. This is a zoom of the falling edge of that switching waveform. We've actually got 100 megahertz ringing on that wave on that edge, which must be coming from somewhere. So that's something that happens in the real world, and I'll explain why in a minute. Under discontinuous mode, I quite like this one because you can start to clearly see there's something in the circuit going on that we haven't really modeled properly yet. Under discontinuous mode, these are the theoretical operating waveforms. So what happens in discontinuous mode is the current in the inductor drops down to 0 before you turn the switch Q on again. And then theoretically, you would then get the switching node actually sitting to be equal to the output voltage. So in our case, about 5 volts. What happens is you get this ringing frequency happening, and then the device turns on again. And if we zoom in and take a look at that, that's about 2.6 megahertz. So there's obviously something going on in this circuit that we haven't modeled in our simple approximate ideal case there. So if we take a first attempt at trying to model some of those non-ideal components, this is what I've done here. So all components in practice differ from those ideal models, whether it's semiconductors, passive devices, whatever, PCB traces. They're never exactly what you want. They've all got parasitics. And it's the relative importance of those parasitic or non-ideal aspects of the devices that have a real bearing on the performance you're able to achieve from your system. So you really need to know about them. Inductors, for example, we've spoken about an inductor just being turns of wire on a magnetic core. Well, because you've got turns of wire next to one another, they will have a distributed capacitance to one another. So you end up getting a parallel capacitance. The inductor winding itself has some resistance, and the core generates core loss. So you can model that as this sort of resonant network here. And the thing is, when you look at the impedance of that component, it'll behave like an inductor at low frequencies. But when you get to the self-resonant frequency, which is governed by the L and the C here, the inductance gives you a rising impedance profile. Then at the self-resonant frequency, it reaches a maximum. And if you go beyond that in frequency, actually the capacitor starts to become dominant, and that inductor behaves to all intents and purposes like a capacitor. So you can't expect it to behave like an inductor above its self-resonant frequency. And similarly, real capacitors, well, yeah, we've got a capacitance in there, but we've also got inductances for the leads that are carrying the current in and out. We've got resistance due to those leads. We've got resistance representing loss in the electrolyte or other storage mechanism. So you get a capacitor which behaves a little bit like this circuit here. And again, at low frequency, it behaves like a nice capacitor. That's great. The impedance goes down as we go up with frequency. And when we reach the self-resonant frequency of this capacitor, it starts to look inductive and the impedance starts coming up again. So if you operate this capacitor above its self-resonant frequency, it looks like an inductor and it can't filter noise anymore. So again, you have to know about the parasitic behaviors of these components to understand how they're going to perform at frequencies that you might not have used them at before. The power semiconductors, there's all sorts of ways of modeling the non-idealities in these power semiconductors. And I'm not going to talk in depth about those. Jose might be discussing some of these different factors in his later webinars. But at a basic level, you could imagine that the power transistor and the diode have a parasitic capacitance across them, which they do. It's specified in the data sheets. The interesting thing with a power semiconductor is that capacitance is non-linear with voltage. So actually you can get some slightly peculiar waveforms in practice that look slightly like a squashed sinusoid. But you can see these components, these parasitic components start to interact, and it's the interaction of those parasitics, especially when the energy has been exhausted in the main passive components. What you're seeing is the resonance of those parasitic components. And then we're taking those components and we're putting them onto a PCB, or perhaps in the case of a much higher power system, we've got bus bars linking everything together. All of those physical connections will start to generate inductance and resistance between components. And whether that causes a problem really depends on where you are in your circuit. So for example, this buck converter, the input loop between the input supply, the switch, and the diode has got a current which is turning on and off incredibly quickly. So if you've got a very high di by dt, you don't need much inductance before you start generating very big switching spikes on those nodes. So for example, if I had 50 nanohenries of loop inductance in that loop, and I'm turning the switch from 3 amps to 0 amps in 10 nanoseconds, that would generate 15 volts of overshoot on here. And that can cause EMI and possible failure if you get things really bad. On the output side, this output loop is less critical, but you still have the parasitics there. It's just they don't really cause you as many problems. It's this input loop on this converter. And it depends on what kind of converter you've got and where those parasitics are. Also, EMI depends very heavily on parasitics, particularly common mode noise. If you imagine this switching node on this converter here, the physical bit of copper connecting the output of Q, the switch, the input to the inductor, and the top of this diode, that's a physical trace on a PCB. That trace, because it's a physical area of copper, if you imagine it's one side of a parallel plate capacitor and earth is the other side of that parallel plate capacitor, and one end of the parallel plate capacitor is moving up and down at incredibly high frequency, what you end up doing is injecting current down into earth through the capacitance that's associated with that, that parallel plate capacitor. So to give you an idea on the magnitude there, imagine this capacitor is only 10 picofarads. That sounds like absolutely nothing. Well, this switching node here on this converter, if it's using a modern power semiconductor device, that could be moving at 100 volts per nanosecond, very, very fast. That would inject currents of 1 amp peak in and out of Earth, and that's purely generating common mode noise. It's one of the most common causes we see of EMI problems. So the key thing is that if you've got very high dV by dt switching nodes, you need to keep the area of those as small as you physically can and away from any earthed circuitry. Otherwise, you're going to start generating EMI problems for yourself. So understanding these parasitics is absolutely key. I'm going to do you a live demo. It's a bit of an experiment. This is a 15 or an 18 watt flyback converter that I've hooked up on the bench next to me here. And I just want to show you some typical operating waveforms from that, just to give you a feel of what happens as we turn power up and down. So this particular one runs at about 90 kilohertz. It develops a plus and minus 15 volt output at up to about 18 watts, but I'm just going to load up the positive 15 volt rail up to about an amp. It takes single feedback from the 15 volt rail. It uses peak current mode control. Remember, we spoke about peak current mode control earlier. We're measuring the current with this sense resistor below the MOSFET in this case. Okay, let me see if I can bring the scope screen up. So bear with me a moment. Sorry. Let's work out how to do this. Oh, yes, there we go. Yeah, here we go. Hopefully that comes up nice and clear. And I will just refresh the screen because this is actually running live. Okay, good. So hopefully you can all see that now. This is it's a flyback converter. It's running about 90 kilohertz. You can see the switching frequency from the scope is highlighted here in the bottom left-hand corner. You're seeing the gate drive, the gate source voltage applied to the primary MOSFET here. So this is going from 0 to about 10 volts gate drive. And the voltage on the top is the voltage on the switching node of that transistor. So it's a little bit like the measurement I made on that buck converter. At the moment, we've got a very small load on this particular converter, but I'm now going to turn on the electronic load and take that load up a little bit. So you can see, actually, it's a slightly unstable load at the moment. Let me wind it up a bit. It's stabilized. There we go. So you can see that as I start to increase the load on this particular converter, load's going up now. We're starting to have a much wider duty cycle. So the controller is measuring the output and adjusting the duty cycle of our switch to maintain the output at 15 volts. If I keep going and going and going, you can see we're just onto the edge now of, in fact, just there is the boundary between continuous conduction mode and discontinuous conduction mode. And if I continue winding up the load, actually the duty cycle doesn't change because of the way this converter, the input to output ratio works. And if I go back down again, turn the load right down or off, you can see we go back to our normal state. So I thought I'd include that just at the end of this presentation to give you a feel of what a real switching converter waveform looks like. I'm a big fan of hands-on practical work with power electronics, and it's always great to be able to share a plot like this to show you a real converter working in practice. So I hope that was interesting. I will just briefly go back to my presentation. Okay. And sorry, bear with me a moment. Yeah, there we go. Okay, so hopefully that was quite a useful demonstration of the flyback converter. In summary, I'd like to just bring this this first webinar to a bit of a conclusion now. All switch-mode power converters, they process energy in discrete packets, and it's the management and manipulation of those energy packets that allow us to control the output of the system and maintain high efficiency. And it's really, the switching frequencies that we're using these days, the management and control of that energy is on a nanosecond time base. It really is that fine with wide bandgap devices. Switching frequencies you might see in practice would probably vary from around a few kilohertz for very, very high power, high voltage converters. And for the board level DC-DC converters that you're using in on your main digital boards, you can get up to multiple megahertz quite quickly as well. Most offline stuff is probably 100 kilohertz or perhaps around about that figure, mainly to do with the EMI standards and keeping the fundamental of that of your converter away from falling in band with those EMI standards. The key part, I think, for any power electronic designer is the more time you spend working on power electronics, the more you start to realize that actually what you're fighting with a lot of the time are the circuit non-idealities and the parasitic effects, which may not be in the data sheet of the components you're using. And this is particularly true as you go up to higher and higher frequencies, where those parasitic effects become more dominant. I do hope you're able to join us for our later webinars. I appreciate today's has been quite a basic introduction to power conversion. Our later webinars are going to be diving into those detailed technical aspects in far more depth. And before I move over to the Q&A session, I'd like to share, I got a new book arrive in the post today. And if you want to have a reference book that I think is probably one of the best out there, this is the new edition of a book from the University of Colorado. This is one of the best books I think that you can buy. In fact, I don't know if I need to reverse my screen. Hopefully you can read that okay. It might be coming out back to front. If you would like that reference, let me know and I'll send you a link to it anyway. But yeah, it's a great book. With that, I think I'll turn over to questions. Okay, so it looks like we've had some good questions online. Fantastic. So I'll start with the first. Can we connect the heatsink to the MOSFET source to avoid issues with EMI? You can. The problem with that is the way most power MOSFETs are made, when you actually look at the way they're packaged, the cooling element is the drain connection. So it tends to be the drain which has got electrical contact to the package of the device, and that's just a bit unfortunate, really. I do remember. I think it might have. I can't remember which company it was. Maybe it was Transform, one of the GaN companies, who introduced a half-bridge pair of GaN devices. And they managed, I think it was them, they managed to arrange it such that the package, the terminal package that you do your cooling with, for the high side was actually the DC link, so the drain connection, but for the low side device was the source connection. And I think that was the case. I'll need to check on that. If you can do that, that does make a real benefit. Otherwise, you've got to be very careful because, as you say, even if you use an insulating material, you've got two parallel plate capacitors. You start pumping common mode current onto your heatsink. And if you start doing that, you've got to think about how you can return that current back to the local power circuit and stop it leaking out into the rest of the world and causing common mode noise. So I hope that answers that one. The next question up: will you be covering bidirectional DC to DC conversion? No, that's a very good question. I will be hinting at it. There is a topology variant of the LLC converter, which allows you to, it's called a CLLC converter, and we'll come on to that in one of the later webinars. But essentially, both sides of that converter start looking the same. And when you start getting into that sort of a system, well, actually, they can be natively bidirectional. So yes, we will briefly cover that, although we don't have anything running on the bench to show you, but there are topologies that you can use to do that. Next question down, how can we choose between continuous conduction mode and discontinuous conduction mode in designing a converter? Now, that's a brilliant question. Thank you for sending that one in. It depends what you're trying to optimize. The benefits of operating in continuous conduction mode is, for a given power level, the RMS currents in your system will be lower. Because if you run in discontinuous mode, what's happening is you're ramping currents up and then ramping them down, and for a period of time you're running to zero energy in your magnetic component. So the period of time where it's not, when it's active, has to be higher to compensate for the period of time it's not doing anything. So CCM is good for high power because it keeps RMS currents down. However, CCM operation has some other performance issues. For example, in an offline mains power supply, if you use continuous conduction mode in your flyback converter, then what happens is when you switch your device on, the device may have quite a high voltage across it, perhaps 400 or 500 volts, something like that. And you've got to discharge the capacitance on that node. If you run that particular converter in forced discontinuous mode, if you remember on the curves I showed you, we saw the resonant ring. There are controllers available called quasi-resonant mode. They actually detect the ring of a discontinuous operating waveform, and they will only turn the converter on at the bottom of that waveform. So that can offer benefits in terms of much reduced switching loss. However, you have to operate in DCM mode to do that. And also, if you're running under no load conditions and you want very low standby, you're by definition you're pretty much in discontinuous mode as well. So it's a bit of a complex answer, really. It really depends what you're trying to optimize. If you're going for very, very high power, though, typically you need to be running in continuous conduction mode because you just can't support the current levels otherwise. So the final question was more about the rest of the series. And yes, there are some upcoming talks. They will be held at the same times and days. And actually, over the course of the next week, I'll be publicising and making available the next block of registrations for those. It won't necessarily always be on a Tuesday and a Thursday, but we're tending to run them at 10 a.m. GMT for a European audience and 5 p.m. GMT to cover some European audience, but also give some colleagues in the US West Coast particularly a chance to join as well. If you do miss any of the webinars, they're all going to be recorded and available on demand afterwards as well. So hopefully that will help. I think that's it now for the questions. Jose, did you want to add anything?
Yeah, there's another question at the top.
Oh, okay. Let me see.
You go. So this DC converter.
Yeah, thank you for pointing that out. I didn't see that one. So
just some seconds ago.
Yeah, okay. So for active power factor correction, there are a number of topologies. If you're talking, and actually if you join our webinar on Thursday, we're going to go into some of those in quite some detail. For single phase systems, you tend to have a bridge rectifier, and then essentially following that is a boost converter, which steps your full wave rectified mains up to about 400 volts, but it pulls a sinusoidal, or it pulls a current which completely tracks your input voltage. So that gives you unity power factor. For three-phase systems, it's done slightly differently, and we'll be talking about those on Thursday as well. In those systems there, you have typically a digital control system and something called DQ control. But in essence, it's a very similar scheme. It's a boost converter type of a converter, but it's just controlled differently. There are some benefits in wide bandgap semiconductors as well that allow you to take the performance of that single phase system and improve it by taking out the bridge rectifier and using it more like an inverter, or it depends how you want to call it. And that's called a totem pole PFC, and we'll briefly be describing that as well. But for those systems, you can get efficiencies of 98 or 99% efficiency fairly easily these days. And I think there was one other question. Yeah, are you going to cover loop compensation topic of a switch mode power supply? The answer is yes. That's when I'm going to be getting into my S-domain modeling and all that sort of stuff. And we're going to talk about that from a perspective of analog and digital control. That is in one of the webinars that we haven't actually opened for registration yet. It's a bit further down in the series. But yes, we will be talking about loop compensation because it's critical that we make stable and robust control loops. So I think
that's it.
Yeah. So that's great. I think we ran over a little bit today, but thank you very much for joining, everybody. I do hope you found it useful. Go out and buy this book because you won't regret it. It's a fantastic book. It just takes a bit of reading. Thank you very much for joining, and we hope to see you on a future webinar. Thanks for now. Bye-bye.